Okay. So we are going to see now, well, first of all, how to use the toolchain. So the software components that you have seen that Ben presented, they map one-to-one to command line tools, which you can use. We are going to see how. And then how to integrate this workflow together with existing model code, with simply the assumption that this model code would be the driver, would work also as driver code. We will see in a bit what that means. In our case, so in the case of ESiWACE, we are focusing on icon. We are trying to get support for to integration of DSL and icon. But in general, we can say that this model code could be written in any general purpose language, C++, FORTRAN, whatever. So again, back to the overview. I'll just briefly recap this. You have these three components, dusk, dawn opt, and dawn-codegen. They communicate through these intermediate representations. Maybe one addition that we can say is that dawn opt, for example, can also take the internal intermediate representation, because you can apply optimizations on top of an already optimized IR. So you can select which optimization you want to enable or not. And dawn-codegen can also output headers and interface. A C header, for example, or a FORTRAN 90 interface. We will see that in detail, of course, on top of the CPP files or CUDA file that are the implementation of the stencils. So let's take a look at how to use the first tool, which maps to Dusk. So you call it, it's called dusk-front. And this will just translate a Python script, rather a Dusk script, which is our Python embedded DSL, into SIR. And it will output that in JSON format on the standard output. Will be the default behavior. And the usage, the standard usage is to pipe these outputs into the next tool, which would be dawn opt to optimize it. But of course, you can also dump it to file to check it out, or for debugging, or for storing, and so on. Errors and warnings go to standard errors, so they don't, let's say, poison the pipe. Then there is dawn opt. This will apply the optimization and produce optimized IIR, again on standard output in JSON format. You can input either SIR or IIR as mentioned, from standard input or from file. Here you have options to tune optimizations, because you might want to enable or disable some of them, or for debugging you could check intermediate states, analysis, and so on. And the usual way to use dawn opt is to specify default opt, the default opt options, which enables let's say the standard optimization, the most stable optimization, we could say. Otherwise, if you don't, you still get valid IIR that you can use for code generation. Also parallel valid that you can use for code generation with the CUDA backend, for example. But it's not going to be as optimized as the one that you get by default opt. It's a bit like specifying different optimizations levels, O1, O2 on GCC, for example. Again, you usually pipe this output IIR into another tool, which would be dawn-codegen, or you dump into an IIR file. So the last tool is dawn-codegen. Of course, it takes IIR in the same way as before. Here we require that you specify a backend. So for example, if your input is an unstructured stencil, for example, if you come from Dusk, you can write an unstructured stencil, so a stencil or on an unstructured mesh. You can select between these two backends, the CUDA icosahedral backend and the naive icosahedral, which work, of course, on icosahedral meshes. So you make the assumption that the unstructured mesh is of icosahedral type. Of course, for broader support of, let's say, general unstructured meshes, you will need another backend. And you can output, of course, so you have to specify a file in which to output your implementations. These will be the implementations, either CUDA or CPP file. Here you can have options to fine-tune the generation for specific, say, GPU architectures. Maybe you want to select the block size and so on. But there are two important options. One is the output C header, which will generate on top of the implementation also a C compatible header, which contains the forward declaration of the run functions. So for each stencil that you have defined on the original DSL code, you will get in this header and in the implementation the functions to run that stencil. And they look like this. These are the signatures. So you first need to provide, well, a mesh. Maybe we will mention that briefly later. And you need to pass the fields, which we also go into detail. Equivalently, you can do the same if you come from FORTRAN and you want to call the same code from FORTRAN. So we can generate compatible interfaces for FORTRAN 90 based on the ISO-C binding module, which is a very standard way to make C and FORTRAN interoperate in the same way you specify which file you want the interface. And they look a bit like this. So if you know FORTRAN, you should be able to read this. Otherwise, it's let's say analogous to a C header. Maybe, yeah, notice that fields here you need to pass as multidimensional arrays. They are then converted to just pointers in C. So overall, to use the tools altogether, it looks a bit like this when you want to specify options. As in this case, you want to output interface and implementation. If you're not interested in specifying options, you can just use the dusk command line tool, which goes end to end. You still need to specify a backend, of course, give an input dusk script, and you will get a generated code in output. Another way to do the same is, say, if you are on a Python shell, you can just call our Python APIs for dusk and dawn, and you can execute these steps without exiting the Python shell. Okay, let's have an overview of now interoperating model code, for example, icon, and well, the workflow that I just described. So for example, say you want to substitute two stencils in the icon style core. We just call them stencil 1 and stencil 2. You would rewrite those, maybe put them into nicely separated files, pass them to dusk, dawn, and ask to generate CUDA optimized implementation and FORTRAN 90 interface. You would compile your implementation with a lower level compiler. So NVIDIA compiler gets a library out of it. And of course, this library will need to be linked at the end when you want to get the executable. These together with the interface and well, also you need some setup tools for the mesh. As you should remember, when you call the stencil, you need to also pass the pointer to a mesh object. This you can generate at the beginning before even running your time stepping, for example. You can set up the mesh and do the necessary conversion from the model format to the one that is understood by, let's say, the generated code. And maybe you have other utilities like for verification and so on. So these all together, what we call interoperability layer, FORTRAN C interoperability layer. And from your model code, you can drive the execution of your translated stencils by just calling the interfaced, now interfaced functions. So this is how we envision interoperability between the model code and the DSL world. Ideally, at some point, this would, let's say, simplify. Ideally, you could just call a dicor function, a dicor stencil, and this will just run the whole dicor as a component in the DSL. But of course, we are not yet there. So now an example visually, let's imagine this code. We extracted this from ICON and simplified. Say you are in a subroutine and you want to compute a gradient. So there is this gradient function written in FORTRAN, and you want to substitute that with a DSL translation. So you will write the same stencil, the same code in Dusk, and then call the toolchain to generate it into implementation and interface. Then use the compiler to compile the implementation into a library. And then you just change your call to now point to the subroutine that is interfaced here, which should do exactly the same as the function before, going through all these steps, of course. And yes, basically this is how you would substitute model code with DSL-ified code. So maybe it's worth mentioning that there are other problems, let's say other requirements when you want to interoperate an existing model which has clearly a specific format of fields. So how these fields are, what is the layout of these fields in memory, for example. You want to ensure that the code that is executing on the DSL side is compatible with the format of fields. And this you can achieve into different alternative ways. You can either do a format conversion, but you will need to do that each time your driver calls a stencil. So before running the DSL stencil and after, for example. And this, of course, comes with a considerable overhead, especially if you do, let's say, a fine-grained rewriting, a fine-grained translation. You incur in a lot of overhead due to this format conversion. The other way is basically adapting your code generation to produce code that already understand the format of your model. And this clearly you will need to do as a parameterization, as you still want to be general. I mean, the compiler still, the compiler and the DSL still want to be general and not specific to one model. But of course, as an intermediate step, so far we just understand the let's say the format of icon and generate CUDA code for, in the same format as icons. But of course, we could always allow parameterization of, say, the dawn-codegen component to adapt to this. Okay, maybe another point to mention is about how we envision to again to substitute icon code with DSL. So one point is that there is a fork of icon which is OpenACC accelerated, so that already can run on GPU, and it's already optimized for GPUs with OpenACC, and OpenACC and CUDA can interoperate. For example, you can reuse the same fields from the OpenACC side as, and share them with the CUDA code, so you can copy the pointers, for example. And this is a nice feature that we want to use, because it makes it easy to validate, for example, and not to have an overhead in say going from CPU to GPU, so moving data, or let's say in general to do some conversion, as we already understand the icon format. So this is we consider this a reasonable choice for many reasons to interoperate OpenACC and CUDA code, and a nice point to start substituting stencils. So two let's say requirements. One is a real requirement, and the other is more like nice to have. Are that, well, of course you need to validate that your computation is correct, and as I mentioned, this is made easier since you can already look at fields on GPU memory, and for example compare already in there if your code is that is generated from a DSL translation is valid. And the nice to have will be to, while you go through the substitutions, you monitor the overall performance of the die core, and see if you are improving or not. This is something we are also interested in. So we are devising a process in which you can achieve both while maintaining the same instance of code. And maybe, yeah, you can think about having some parameters that are, let's say, compile time, so defines, and if you want verification mode, you can compile the same code for verification. And of course it won't be optimal, but it's a different purpose. And then you just change this define to let's say performance mode, and there you can start monitoring time meaningfully. Yes, that's it. So yeah, this concludes the integration part. If you have any questions, please write them on the Google Doc. Thank you.
Thank you very much, Giacomo. We actually have one question from Rupert, who is asking, is this integration with ICON for distributed memory, or is just a single node optimization? Otherwise, do you generate distributed memory, or maybe payload changes or things like that, or it's just single node?
Yeah, at the moment it's just a single node. For the future we surely need to investigate multiple nodes, multiple GPUs, and so on. So yeah, so far it's single node only.
Mm-hmm. There's another question coming. The question is from Gis. Do you require bitwise reproducibility for validation?
Okay, so far for the stencils we have translated, no, we don't require that. We are good with, let's say, small enough error norms. I would say it's a relative error. I think we said 10 to the minus 12 or something for double precision. But yeah, not bitwise reproducibility. Yeah.
It's also probably fair to say that it's not possible if you validate between different architectures, right, like CPU or GPU. So you're forced to require like a tolerance validation. Any other questions from participants? Doesn't seem to be the case. Maybe one clarification, since we saw a lot from Giacomo for this integration of icon, we will not see much of icon code because it's under license, so we could not share with the entire community. But there are very like similar examples that we took, like in terms of operators. This is what we are going to see starting from tomorrow, all the operators that we can develop with dusk and dawn. Excellent. Thank you very much again, Giacomo. Then I propose we are a bit few minutes ahead of time. That's okay. We can relax a little bit and take a coffee break, an extended coffee break. And then the plan, we're going to stick to the plan of reconvening at 3:30. So when we are going to start with the preparation of the hands-ons and understanding the framework for the hands-on session, I think it's going to be Ben again showing that. Then have a good coffee break, everyone, and see you at 3:30.